Hello everyone, welcome to Dakshana E classroom program. So in last lecture we talked about motional EMF and that in EMI, electromagnetic induction. And in last lecture we saw what is exactly EMI, how Faraday's based on some experiment derived or got some conclusion that we call that we studied as Faraday's law of EMI. So whenever there is some changing magnetic flux is linked, is it, or through a conductor, or some, I will say, a conductor is cutting the magnetic field lines, then always some EMF is induced in the conductor, and we calculated that EMF also. So we studied that in terms of motional EMF. And so when a conducting rod is moving in a magnetic field, some EMF is induced in the rod. We saw the explanation of the EMF induced in the rod. One is by Faraday's law, that is the explanation or the changing flux, is it, magnetic field lines cutting the rod cutting the magnetic field lines. Another was based on the force on a charged particle moving in magnetic field. So when a conducting rod is moving in magnetic field, simultaneously the charged particle means basically electron, charged particle here I mean electron is also moving, and on that electron will experience a magnetic force, and because of that it start accumulating on one end, and that's why on one end some negative and another and positive charge is induced or created, and that result in some EMF in the rod. Let's see some application or one more application. We saw few cases, few application in the last lecture. Let's see one more example based on that, and then we will see the next topic. So let's consider here, this is a conducting rod of length L, and it's given a uniform velocity or constant velocity V. A conducting rod is given a constant velocity V in non-uniform magnetic field, and B is given by this B naught 1 plus y square by L square, where y is the coordinate, y coordinate. So magnetic field and it's pointed outward. This is B. Now here you are asked to find the EMF induced in the rod. So this is also easy, we can straightforward go, and you must be remembering, if there is a rod moving with velocity V, length L in the magnetic field B, then EMF in the rod is given by BVL. That this formula you must remember. If the velocity is given, is it, at some angle, let's say this is V prime at an angle theta, then EMF prime is equal to BVL into sine theta. So this you should remember. Now see here, actually what I can do here, because B is not constant here, so what I can take a small element of this rod, is it. So let's consider small element of the rod. So let consider a small element of rod. Okay, so this is a rod, and I am taking this is complete rod. I am taking a small element of this rod at distance y, and this length is dy. Okay, so this element I am considering. Now you can see this element is given some velocity v, its length is dy. So I can write the EMF induced in this rod, that is dE, is equal to what? B into V into dy, BVL, right? And B is what here? B is given by B naught into 1 plus y square by L square. I can substitute, so D EMF is equal to V B naught 1 plus y square by L square multiplied by dy. Clear? Alright, we can even decide its polarity. So for that I told you, you can go with the right hand thumb rule. And what is that exactly? Or simple terms, you can go even with the cross product also. So this is a small element, it's moving with this direction. You can just check the force on electron, and force is given by Q V bar cross V bar. So you can see like velocity in this direction, and here magnetic field is in outward direction. So V cross V will be downward. Is it? V cross V will be downward. So the force on positive charge will be downward, on negative charge. So the polarity of EMF will be this way actually here. Is it? So overall in the rod, downward will be positive, upward will be negative. This is the EMF. Complete EMF we can just simply integrate it. So 0 to E, and this is 0 to L for length. So this E EMF is coming out to be V B naught, and integration of this will be Y plus Y cube by 3L square, substituting the limit 0 to L. So if I am substituting 0, everything will be 0. On substituting L, here L cube by L, so it will be like, I can write V B naught L plus L cube by 3L square. So this is also L by 3 plus L, so that it's 4L by 3, and we are getting this is 4V B naught V L by 3. This is the EMF. So you can see very easily we can get the EMF in the rod, or induced EMF in the rod. We call it motional EMF because this is arising due to the motion of rod in magnetic field. So if magnetic field is uniform, we can directly write VBL. If magnetic field or something is non-uniform, then we need to go for integration part. So I hope you are clear with this part. Let's see the next topic, that is EMF due to rotation of rod. Okay, so the next topic is EMF due to rotation of rod. The last was motional EMF, means when a rod is moving in magnetic field, then EMF is induced in this rod, and we calculated that. We saw some example based on that. Next is EMF due to rotation of rod. So means here what is there, if a rod of, let's say, length L is rotating in magnetic field, for the simplest case, easy to understand this concept, I will be taking the magnetic field here uniform, is it? So in rotating in magnetic field, right, with, let's say, angular speed omega, then EMF is induced in the rod, and that is called EMF due to rotation, is it? So let's calculate what will be that EMF and why. We can even understand that too. So I hope like why reason we have already got it. So let's consider here we have this rod. This is a rod of length L, hinged about this point, rotating with angular speed omega, and there exists magnetic field, uniform magnetic field in complete space. So let's say B is the uniform magnetic field in this region. So here it's complete region, here, everywhere, wherever the rod is there, at least in that complete region, magnetic field B naught is there. L is the length of this rod, omega is the angular velocity of this rod. So this rod is rotating like this. This is the hinge point, it's rotating like this. So now some EMF will be induced in this rod, and let's calculate that EMF. Okay, so one way is just look at it. Here what I can do, I can consider one small element of this rod. So let's say this is the small element at distance r, length dr. Now you see this length r, like dr length element will have some velocity in this direction, that is v, and that is equal to r into omega. So this element has length dl, that is equal to dr, velocity v r omega, and magnetic field present is v naught, and you can see here velocity is perpendicular to its length, is it? So let consider a small element of rod of length dr at distance r from hinge point. Okay, So this is our setup. So now here you can see for this small element, I can write its velocity is equal to r omega, length is dr, and magnetic field present is b naught. What it implies, I can write EMF induced in the rod, EMF induced in this small element can be written as DE is equal to what? It's BV into L, and B is B naught, velocity is R omega, length is dr. Simple, right? Next, total, I can just get it integration. So total EMF, this implies total EMF E and length is 0 to L. So integrating it, it's coming out to be EMF, and this is B naught into omega. Integrating R square by 2, substituting the limit that you can directly understand, we are getting this is the expression of induced EMF in the rod. Next thing, again the polarity of this. So polarity, you can just consider this small element, its velocity is downward V and magnetic field is inward. So force on positive charge particle will be V cross B. Velocity downward, magnetic field inward. V cross B will curl finger in the direction of B. So V pointing in the direction, pointing my fingers in the direction of velocity, curling my fingers in the direction of magnetic field, thumb is giving you the direction of force on positive charge particle. So here what will be the force on positive charge particle will be this way, and this is negative. So the polarity will be this way, right? So this end will be like positively charged, this will be negative charge, polarity will be this way, and EMF is given by this. So EMF on a rotating rod in uniform magnetic field B naught with angular speed omega having length L is given by EMF is equal to B naught omega L square by 2. So this is EMF due to rotation of rod. That is the concept. I hope you are understanding this. It should be clear to you. Let me explain the same expression in different way also. So another way to understand this is, let's consider this is your rod of length same L and hinged about this, rotating in with angular speed omega, and there is again uniform magnetic field B present in complete space. So this is our system, right? So now I will say, let the rod rotate for small time dt. Is it? In this case, so rod, if it is rotating for small time dt, then final initial position, this will be the final position, and this is angle theta described by the rod. So I can write theta is equal to what? Omega into dt. Clear? This is, so now you can see, now in this case it's like cutting some magnetic field lines, or there will be some change in flux, is it? So I can write the change in flux due to rotation, that is equal to B multiplied by area swept by rod in time dt. Clear? So this will be the change in flux, and change in flux divided by dt time, because this flux is changed in time dt, will be the d phi by dt, and that, so I can write this quantity is equal to d phi, and d phi I can write is equal to B multiplied by, so B is B naught into, what is the area? So I can write this is what, a arc, is it? Like you can say one part of the circle, and its area is, if like we know for total circle area is pi r square, so I can write it's theta upon, it's will be like 2 if we are writing theta in angle, like theta upon 2 pi, just 1 second. Okay, so theta I got already omega into dt, so then I can write it's half of theta into r square, is it? because if it is completely like rotating one circle, then theta will be 2 pi. So half of 2 pi into r square will give you area, right? So here I can write area swept. So this is the area swept. Area swept can be written as half into theta into r square. So this is equal to half theta is omega dt multiplied by r square. So this is d phi. Then this implies EMF induced is d phi. Here I am writing magnitude. Remember that is d phi by dt. The polarity I have already shown you, and you can even check it here also exactly in same manner. So this is equal to d phi by dt. Now here if I divide simply by dt, dt gets cancelled, and you can see it's coming out to be b omega r square, or sorry, here r is equal to L. So I will write r is equal to here L. So this coming out to be b naught omega L square by 2. This is the EMF induced. Clear? So this is another way we can understand, that is by Faraday's method of change in flux. So in a rotating rod, if it is rotating in uniform magnetic field or magnetic field also, then EMF is induced, and we got the expression that is given by B naught omega L square by 2 is the EMF induced in the rod. Let's see some application based on this concept. Okay, so let's see one problem. A rod PQ of length 2L is rotating about point P with constant angular speed omega and uniform magnetic field B naught. If the EMF induced between PQ is 100 volt, find the induced EMF between M and Q, where M is the midpoint of PQ rod. So this is the diagram given to you. PQ is a rod which is being rotated of length 2L, rotated with angular speed omega in uniform magnetic field B naught about point P, and EMF induced between P and Q ends is given by 100 volt. This is, and now you are asked to find the EMF between M and Q. So I got actually EMF E between PQ is equal to 100 volt, and I can write E PQ is equal to what? B naught omega L square by 2. That comes out to be 2 B naught omega L square. This is 100 volt. Clear? And I can also write E PQ is equal to what? E PM plus E MQ. Right? This total potential difference between PQ is equal to what? E between this plus that, adding both of these. And here, remember that between, if I'm just removing this part, then it's rotating with angular speed omega length L about B. Then I can write E PM will be equal to what? B naught. This is B naught omega L square by 2. Clear? So this is, then I can substitute it here, right? So this implies, let me substitute it here. So total is this, that is E PQ is equal to 2 B naught omega L square E MF PM plus EMF MQ, and this I know that is P omega B naught omega L square by 2 plus E MQ. So by substituting here, I am getting the value of E MF MQ is equal to 2 B naught omega L square minus B naught omega L square by 2, and that comes out to be EMF MQ is equal to 3 by 2 B naught omega L square. Clear this? And I know the value of B naught omega L square. 2 B naught omega L square is 100, so B naught omega L square is 50, so that I can substitute it here. E and Q is equal to 3 by 2, and this is equal to 50. This implies it's coming out to 75 ohm. That is your answer. Right? So simple thing, like there should not be any confusion. We know about like EMF between P and Q is given by that this in terms of numerical value expression is given by P naught omega into its length whole square. Length is 2L, substituting we are getting this expression. EMF between M and Q, remember this here, the thing is that this rod is there. So if I am rotating it about this end, then EMF between these two ends can be written as V naught omega L square by 2, is it? But EMF between these 2 points, is it? I mean here, just simple thing. Let's say this is again PQ. So it's rotating about this, and if total length is L, then I can write magnetic field B. It's V naught omega L square by 2 between 2 ends. But if I take this M point, then EMF between this point and this point, it will not be exactly half of the total EMF. Remember that. And it's even proving this. Because EMF between these 2 ends will be, if I take its length is L, just imagine this. Let me say it's only this. This is the PM length and its length is L by 2. Then EMF between P and M, EMF between P and M is given by V naught omega length by 2 whole square divided by 2. Okay, and this comes out to be V naught omega L square by 8. So you can see it's not half of EMF between P and Q, right? And that's why it's little bit difference is coming. So you just need to take care of that. Remember that point. Let's see some more cases here. Okay, so let's see next problem. That is a rod of length L, resistance is small r, is rotating about one end as so. So this is a rod of length L and resistance R, rotating about this end with angular speed omega, and its other end touches a conducting ring. So this is a conducting ring of negligible resistance. A resistance capital R is connected between center and periphery. A resistance capital R is connected between center and periphery like this. Draw the electrical equivalence and find the current in the resistance. So draw the electrical equivalence of this system and find the current in the resistance R, and there exists a uniform magnetic field V naught directed into the base of inward like this. So this is the problem given. It's easy. Let's see how it works. First you need to understand the problem clearly. So here you can see this ring is conducting and having negligible resistance. So if I just forget about complete system, magnetic field is B and this is a rod of length L, angular speed omega about rotating about this end. Then what I can write, EMF induced in the rod, EMF induced in the rod can be given as what? So it's coming out to be V naught omega L square by 2. Another thing is the polarity. Polarity of this EMF will be what? So you can see its velocity is V is this way. So V cross V, so this will be the positive end, so the polarity will be this way. Right? EMF is this. This rod is having resistance R, then I can just simply, if I convert this system, then I will get it this way. Is it? So here it's what? This is having EMF, some resistance connected, and this capital R, this is capital R, small r, and this is EMF E, like that. This is the circuit. Remember, this is a conducting wire. This is a conducting wire. So actually I can just fold it backward, and it's simple, one wire, like complete. So it is not having any resistance, and like you can just simply like flip it and make it small and merge on it, right? So this system equivalently can write this way, this, and right. So this is capital R, EMF, small r. This wire you can just hold it here, and it's like conductor. There is no resistance. There is resistance. Then yes, there will be difference in the circuit. But otherwise, if there is no resistance, I can merge these two wires also. It will be like still same. So if I am merging them, then equivalent circuit will be simply this, this is resistance and another resistance, and this is a conducting wire R, EMF E and capital R. This implies current I in the circuit is given by EMF divided by total resistance capital R plus small r, and EMF is V naught omega L square divided by 2 divided by this resistance R plus R. So I current is V naught omega L square by 2 capital R plus small r. This is answer. Right? So I hope you should be understanding this. There is no there should not be any confusion. Simple thing. A rotating rod is equivalent to a EMF, but it is also having resistance, so that will be connected in series. You can connect this resistance here also. It will not be a difference. It will be still same, and we can simplify the circuit. It's coming out of this and that, and simple circuit. Two resistance in series are equivalent EMF this, so current is E divided by EMF divided by resistance, total resistance, right? So this is one problem. Let me just write another problem by just modifying it a little bit. Okay, see another problem. It's just similar to the last one, small modification. So here the length of the rod is actually 2L. It's touching both the ends at rings. Both ends are touching, and center is at the center of this ring. And resistance is R. So with 2 R's, which means this part is also having resistance R, and this is also having resistance R. This is capital R, and this ring is again conducting with negligible resistance. And for this system also, you are asked to find the current in this resistance R and the equivalent circuit. Okay, so let's see here. So first thing is, I can separately deal. This part is rotating with angular speed omega, length L, magnetic field B is also present. So I can write there will be EMF induced in this, there will be EMF induced in this, and the polarity for this part will be this way, polarity for this part will be this way. Because you can see here the velocity will be downward, so I can write B cross B, then this will be positive. So the equivalent circuit, first thing is EMF. So EMF E can be simply written as what? V naught omega L square by 2. This is the EMF E, right? Here, and this is also E. Now, if I draw the electrical circuit of this system, that will be it is having resistance, EMF, center, here EMF, resistance, and this resistance. R, smaller, and this is E and E. And remember, E is equal to this V naught omega L square by 2. And conducting wire. Now see here actually. So if I am marking this is point O, then you can just see this is completely one point. Is it? So let's say this is point P. Then this is P, this is P, this is P. So actually in this system there are 2 points. Means points having different potential is only 2. One is this, another is this. So if I just write this system, then it will be O point here, and let's say P point is here, P and O. Then in between O and P, I can write one is this, right? E R. Let's say this I connected simply here. Another, this is also P point, because here potential complete ring is same because no resistance. So O P. So O not Q, it's O. So O and that point is P. Now OP I connected one. Now O and P. So O again at high potential, resistance, and P. So I'm connecting with O another. This is O, P and resistance R. Connected this way. And O and P, another resistance here. So this is resistance R. So this system is equivalent to that. And here there are 2 cells, you can write this, and by combination of cells I can write this system is also equivalent to one resistance and EMF equivalent and R equivalent. So R equivalent will be R by 2, resist EMF is E and it's capital R. and E is equal to, remember, V naught omega L square. So this system reduced to this system, and finally this. Here I have combined this by combination of cells in parallel. Then if you just combine it, you will get resultant EMF and resultant internal resistance or resultant resistance. So now from this diagram I can write the current I is coming out to be V naught omega L square by 2 divided by capital R plus R by 2. This is the current in resistance R. So I hope you understand this part also. So this is another example. So like that is also here you can see there is EMF induced in the rod due to its rotation in magnetic field. Let's see some more cases based on it. Okay, see next problem. So a rod of length L is rotating with angular speed omega about one of its end, which is at a distance A from a infinitely long wire carrying constant current I. So this is infinitely long wire carrying constant current I. From this wire, a rod of length L whose one end is at a distance A from this wire is rotating about this end with angular speed omega. Find the EMF induced in the rod at the instant shown in figure. So at this moment of time, what will be the EMF induced in the rod? Okay, so again here we can see it's the EMF induced in a rod due to rotation, right? So we have already derived the expression. Another way is because B is not constant here, so that's why I can't write the simply expression as B naught omega L square by 2. So for that case, whenever something is varying continuously, definitely we have to go for integration, and in integration we will consider small elements. So let me consider from this end at a distance x a small element of length dx. So I hope this part is visible. Its length is dx and this distance is x. So the distance of this small element from the wire is a plus x. Then magnetic field B is it? Let consider a small element of length dx from end of this rod at distance x. Okay, so now I can write magnetic field B at the position of this element can be written as B is equal to what? That is mu naught into I divided by 2 pi x a plus x. I got B. Now velocity of this is what? X into omega. So EMF induced in this wire in this can be written as EMF is equal to, so dE BVL, right? EMF I can write, so B I got, V velocity we have, velocity of this small element will be, it's right, velocity you can write x into omega. So velocity I have, length I have, then I can substitute simply here. So it's B is mu naught into mu naught times I divided by 2 pi a plus x into velocity x omega into length is dx. Next is integration of this we will get, and what will be the limit of this integration? So limit x we are measuring from here to there, so x will be 0 to L, so it will be 0 to L, and EMF E, so this is mu naught I omega divided by 2 pi integration, this is x dx divided by a plus x, and 0 to L. So for integration part I can add a and I can like subtract, so this system can be written as mu naught I omega by 2 pi and integration, so this is x plus a minus a divided by x plus a this whole multiplied by dx and 0 to L. So now if I just, you can see this is what? X in the numerator, so x plus a divided by x plus a, that will be 1, and it's minus a by x plus a. I can further simplify, it's mu naught I omega divided by 2 pi. It comes out to be integration of 1 minus a divided by a plus x, this whole into dx, limit 0 to L. I can further, so it's mu naught I omega divided by 2 pi. Integration of 1 will be x, and substituting the limit I will be getting it's L minus a is simply taken out, constant. Integration of this will be ln a plus x, and substituting the limit I am writing it directly a plus L divided by a. So this is your final answer of EMF induced in the rod at this moment of time. So I hope you are clear with everything. We got the expression of magnetic field at this, because we are considering this is a small element. So for this small element I can almost consider the magnetic field B is uniform or constant. Length I got dx, speed of this small element is x omega. Substituting B, V, L, dE, substituting, integrating, we are getting the answer. So that is next problem. Okay, so see here we have another problem. A uniform rod AB of length L and mass M. So this is AB is a rod of length L and its mass is also given as M. Is placed over two conducting rails PQ of negligible. So P and Q are these two conducting rails, okay, of negligible resistance. If switch is closed at t is equal to 0, so this switch is closed at t equal to 0, and the velocity of this rod initially at t is equal to 0 is also 0. Resistance are connected this way and one battery this way. So this battery, switch, resistance and this rod is actually completing the circuit at every instant of time. Like initially the rod is here, after some time the rod will be here, so again the rod, this will be the completing the circuit. Okay, so this is the system. Now you are asked to find the velocity Vt of the rod AB as function of time, and also find its terminal velocity, terminal speed, and uniform magnetic field B naught is present in this space. So this is the problem. It's little bit complex, but pay attention properly, then you will be understanding it. It's like not difficult, but little bit you can find it lengthy, because other problem was straightforward and easy. So that's why compared to those, it will be little bit lengthy, but no need to worry, just pay attention properly, you will get it. Okay, so let me just first explain you what is exactly happening here. So in this situation, initially rod AB is at rest, right? So now what will happen when I'm switching this on, battery, resistance, and here this rod, it has like resistance also 0. So what will happen? Some current will flow in this rod AB, and AB rod having current I placed in magnetic field will experience a magnetic force. So you can see the magnetic force will be like I is downward, right? I, so we can write L cross B. So L cross B, so you can see the force, magnetic force on this wire will be this way. Magnetic force ILB, is it? So because of that, this rod will start accelerating or moving, will gain some velocity, and you can see as it will gain some velocity, what will happen actually? Some EMF will be induced in the rod also, and that EMF, so we can get the velocity V cross B. So the EMF polarity will be upward, polarity of the EMF induced in the rod will be this. So this will further affect the current in the circuit, and finally at some time t, the rod will be moving with some velocity V that we need to find, and maybe after some time the rod is moving with constant velocity, we need to find that velocity also. We will be assuming these rods P and Q are infinitely long, and this magnetic field is also present in complete region. So I hope you understood that what is exactly happening in this situation. Next thing is, let's solve it, how we can approach, how we can find the desired result. Okay, so let me write here, let the situation at time t. I am here talking about the situation at time t. So what will happen actually at time t? The situation will be, this is the circuit, resistance, this is your rod, which is having some velocity v and some current I is flowing in this. So you can see velocity and force, how much magnetic force will be ILB, magnetic force on this rod AB, okay, and EMF, and some EMF will be also induced in this wire, and let's say this is E prime, and that is equal to what? This is equal to B V T B naught into velocity function of time into L. So this will be the EMF induced. So at time t, the situation of this circuit will be, this will be constant, resistance will be constant, this is R, some current will be there, that will be also changing. Another thing is velocity will be there, and this rod will experience a magnetic force, and some EMF will be induced in this rod as it's moving in magnetic field. So that EMF is given by this, because this velocity will be changing with time, right? So now in this circuit, what I can write? EMF, I can write, if I apply KVL, so if I just go this way, then EMF I can write directly, it's E minus E prime divided by R is the current, and this is E minus B naught into VT into L divided by R is the current I. Clear? So this is the current, force on this and velocity is this, both are in same direction. So I can write magnetic force on rod AB, so that can be written as I is this, remember that, L into B. Clear? And I can write this magnetic force is equal to what? Mass into velocity of this rod, means acceleration, dV by dt. So this is equal to I, and I can substitute this, so let me write I L B naught, and I is equal to E minus B naught into velocity function of time into L divided by R, I L B naught. Clear? M dV by dt. So now I can rearrange it, and I will write the velocity term here. So I am writing this V, simply V is not constant, it's changing with time. This implies I am getting the expression, this is M dV, and this term I am writing here down, so it's E minus B naught L V, this whole multiply, here it will be L B naught by R, and I can divide this also there, then it's MR multiplied by dt. So I hope you are getting it up to here. This next we need to integrate it. For that I can erase this part. I hope you have understood the question. So I need some space to simplify it further. Alright, so that is the space now I will be using. So I hope you understood. Simple thing, I got the current, this is the situation of circuit at t time, expression for the current, getting this magnetic force ILB, and force is equal to MA, A is dV by dt, and getting an expression this. Velocity and this here velocity terms I am dividing it here, M here, LB naught by R there, so this I am getting. So here expression 0 to t, and velocity I know it's actually 0, 0 and t it's V. So integration on this side will be like, I can write minus 1 by B naught into L, and this is ln E minus B naught L V, this limit 0 to V. On right side it will be L B naught by M R into T. Clear? This part can be multiplied further there and substituting the limit, so it's I am getting ln E minus B naught L V divided by, substituting V, then it's this 0, then it will be E, and here multiplied, so it's B naught square L square divided by M R into T minus. Clear? Ln, if I am removing it, then it will be an exponential multiplied by this, and simplifying it, so I am getting it's I can write it this, so we are getting it's basically it will be e power, and so e I am taking it out, divided by b naught into L. It's 1 minus e raised to power minus b naught square L square into t divided by mr. So this is the expression of velocity, or this is the result, which is the velocity function of time. So one result we got. I hope, just simplifying it, you will get it here actually, right? Next thing is terminal velocity. Terminal velocity means terminal velocity. So one way is you can write at t is equal to infinity, that finally at infinite time with what velocity this rod will be moving. If I substitute here t is equal to infinity, this will be simply 0, and your vt, terminal speed, is coming out to be e divided by b naught into L. This is the answer for terminal speed. So I hope you understood this question. It's little bit difficult, you may find it. I think, like, according to me, it should not be difficult, but if you are not focusing, if you are just missing some part, then you may face some problem. Okay, let me still explain it again. So we got this situation, this system at t time will be equivalent to this EMF, circuit complete resistance, and here some in the rod AB some EMF will be induced given by this velocity at time t is v. Force will be acting on this ILB, and I is the current in the circuit. We write I net EMF divided by resistance, this. Force ILB, and force is equal to MA, and MA is equal to ILB A hybrid and dV by dt, because ultimately we require the expression for velocity of that rod AB as function of time. So we got this expression, and I substituted again here, and then we got this relation. Then we simply simplified it and wrote it in the integral form. After integrating it here, we are getting this expression. Simplifying it, we are getting this expression. Terminal speed means, or terminal velocity means, velocity of the rod at infinite time or after long time with what velocity that rod will be moving. So we simply substituted t equal to infinity in this expression of velocity of function of time, and we are getting the expression for velocity at infinite time, and that is termed as your terminal velocity, terminal speed. So this is all about this problem. So I hope you understood this part. Okay, see few more cases. A conducting ring of radius r rotate with angular speed omega about an axis perpendicular to its plane and passing through its center. So this is the axis perpendicular to its plane passing through its center, and this ring is rotating with angular speed omega about this axis. A uniform magnetic field B naught is also present everywhere. So in this plane B naught is present, and that is directed inward. Now you are asked to find the EMF induced in this ring. Ring is rotating, is it? So now see here, actually the flux through the ring, what can be written? So phi is equal to what? B multiplied by its area. So that is B into area is pi r square. Now see here, this ring is rotating like this. So in this rotation you can see the flux through the ring is remaining constant, it's not changing, and we know when there is no change in flux, no EMF is induced in the ring or any conductor. So we can say here, as ring rotate but the flux through ring remains constant. Means flux is not changing, so this implies EMF induced will be 0. So no EMF will be induced as there is no change in flux, right? Okay, see another case, we have another problem. So ring rotate with angular speed omega about an axis in the plane of ring passing through its center as shown. So now this is a ring and it's rotating but about an axis. This is the axis. So this ring, this is the plane, it's rotating like this actually. It's rotating about this axis, and uniform magnetic field B naught is also present, directed inward. Now here also you find the EMF induced in the ring. So what do you think, whether there will be some EMF induced in that ring or it will be also 0 in that case too? Just think about it and you will see that actually in this case, when the ring is rotating, flux through the ring is changing. Why? You will find flux is changing because you can say the angle between area vector and magnetic field is changing. You must be remembering I wrote the phi is equal to b bar dot a bar, so that is equal to b a cos theta. Is it? So here it's something new, something different. Here what is happening? B is the magnetic field, not changing. A is the area of this plane, not changing. But what is this? So means even if theta is changing, then also flux can change, right? So even if theta is changing, then also flux can change, and that can also result in induced EMF. So in this situation, actually B is not changing, A is not changing, but theta is changing, and because of that, flux through the ring is changing, and that result in some induced EMF in the ring. So now the point is next, how we can find that and what will be that EMF. Okay, so just try to imagine it. I will try to. So look at it. So here magnetic field is directed inward. Okay, and this is the plane of the ring. So if you just look at it, plane of the ring, and it's directed this here. So if you just look at it from like the front side, then ring will appear. This is the ring. It will appear just like a plane wire, and magnetic field will be like this. Is it? So if I look at this diagram from this side, let me draw its diagram. Is it? So view of ring from left side. If I look at it from left side, this is left side, right? So this is like right, left. So this is I mean this side. Then what will happen actually? Your ring will appear like this. This is the ring, and magnetic field is what? Directed inward. So magnetic field is directed this way. Okay, so what is this means? Here I can write in this situation, this is at t is equal to 0, so I can write phi is equal to b into a, and you can write b into pi r square, because magnetic field, like if I write let me write, if I take the area vector outward, area vector, is it a bar, then it will be minus, you can write it's minus b into pi into r square. Here I am more interested in magnitude. Okay, so now this is the situation. Now just imagine this ring is this, it will be rotating about this axis. You can just imagine this is a ring, it will be rotating like this. So if you look at it from this side, then it will be rotating about this axis. So exactly same thing here. So it is this, and it will be rotating like this. So after some time, if this is the axis, the ring will be like this way. Just 1 second. So ring will be rotating like this. Sorry, diagram is not. So here I hope you are able to imagine the situation, how magnetic field lines are directed inward and how this is rotating the ring, and I am saying this is a rotating ring and this will be some angle. So I will write, okay, the thing is here I am writing this angle as theta. Okay, and it's okay even if I take this angle as theta, that is also right. So here theta will be equal to what? Omega into t. Clear? Only the expression will be, instead of cos theta, it will be like coming in terms of sin theta, but there is nothing wrong in that too. So now at t is equal to 0, this is the flux. Flux at t equal to 0. But at time t, the orientation of the ring will be this way. So here area vector of the ring is this, right? And this is the magnetic field here directed this way. So the angle between area vector, this is the a bar at time t, this is the angle between a and magnetic field, and this will be also theta. So this angle is pi minus theta. Clear? And here now I can write, so the flux at time t, flux through ring at time t, this phi can be written as b dot a, and that will be equal to b into a is pi r square into cos of pi minus theta. Clear? And this you can write minus of b into pi into r square into cos theta. So this is phi. Clear? Now you can see, and theta is what? Here theta is this, you can write minus b pi r square into cos of theta is omega into t. Clear? So now what is the, you can see here, this quantity is changing, pi r square not changing, b is not changing, omega t is changing. Now if I differentiate it, so EMF induced, EMF is equal to minus of d phi by dt, but here I am more interested in magnitude, and that will be coming out to be, if I just take the negative sign, then it will be minus minus plus, but differentiation of cos will give you another negative, it's minus b pi r square omega, and differentiation of cos is sine of omega t. So this is the EMF, and here you can see it's sinusoidal EMF, means here the EMF induced will be changing with time. So here sine function, and at t is equal to 0, so it will be like starting with this way. So this is the EMF versus time graph, and we are getting, this is the expression. I hope you are understanding. So the point is that we got ultimately flux means phi is equal to b into a into cos theta, where theta is the angle between magnetic field and area vector. So now if b is changing, then also we get EMF. If area is changing, then also EMF is induced in the conducting rod or ring, whatever it is there. And even when theta is changing, b and a both are remaining constant, even when theta is changing, then also some EMF is induced in the rod, and we can see the example here. So this is the EMF induced in the rod. The magnitude will be simply b pi r square omega into sine of omega t. So this is about that problem. Okay, see here we have one more case. Figure shows a wire frame PQST XYZ placed in time varying magnetic field B. B is here time varying, it's not constant, that is given by beta into T, where beta is a positive constant, and resistance per unit length of the wire is lambda. So this is the situation, and find the current induced in the wire and draw its equivalent electrical diagram. So here situation is two square frames. This is a TXYZ and this is PQST. So two square frames and placed like this. So one wire is actually like banded in this shape, and uniform magnetic field B is sorry, not uniform, it's time varying magnetic field is present in both the cases. So now what will happen? See, through this flux is there, but flux is changing here because of change in magnitude or change in magnetic field. So that will also result in changing flux and EMF will be induced. So let me first calculate EMF induced in this like wire and this wire. It means basically this loop, let me write, this is a loop loop 2 and this is loop 1. So I can write EMF induced in loop 1, because phi is equal to what? Phi 1 is equal to, it's beta t into a square. So EMF E1 is equal to d phi by dt. I am writing here magnitude, that is equal to beta into a square. This is the EMF. Similarly in loop 2, so this you can write phi 2 is equal to what? It's beta t into area b square. So EMF E2 is equal to beta into b square. So I got basically EMF induced in both this and that. So it beta a square and beta b square, right? And here it's given b is more than a, bigger than b, so means this EMF is bigger. So next point is, what is the polarity of this EMF, right? So now see here, this is the loop, this is a frame. Through this magnetic field is pointed inward and it's increasing, beta positive constant, so with time magnetic field is increasing. That implies flux through this is increasing. So what will happen actually? The EMF should induced in a manner such that it should oppose that increasing EMF, increasing field or increasing flux. So what will happen? If current is flowing this way, then that flux will be outward and that will oppose the inward flux. So here I can write the polarity will be this way. Similarly in this case, here flux is also increasing, right? So here also the polarity should be up like this way. I mean like current should flow anti-clockwise, so the polarity will be here this way. So this is E1 and this is E2, right? And this wire will have some resistance like lambda, or resistance per unit length is lambda. So this frame will have resistance of 4 lambda into B, and this will have resistance of 4 lambda into A. So now equivalent circuit I can write, it's basically this circuit, it's battery, and here I can connect the resistance this and this way, and here the battery is connecting this way, and let me write resistance here. So this is 4 lambda A, resistance 4 lambda B, and it's E2, that is beta into B square, and this is E1, that is beta into A square, right? Now I can simply apply KVL in this loop, so I can go from here. So the current will be definitely, because this EMF is greater, so current will be flowing this way, this way, this way, and this way. So you can see the EMF, they are opposing actually. Here it's positive, like we are going from negative to positives, high increasing, and it's reducing. So effective EMF will be this minus this, effective resistance will be it will be in series, this plus that. So I can write simply current I is equal to, you can write E2 minus E1 divided by total resistance R equivalent, and I is equal to, this is beta, that is B square minus beta A square divided by 4 lambda A plus 4 lambda B, and finally we are getting, so here from here you can take A plus B out, is it, and B square minus A square, so this can be written as beta, B square minus A square can be B plus A, B minus A, and divided by 4 lambda B plus A, this cancel out, and this I am getting I is equal to beta B minus A divided by 4 lambda. This is the answer. So here you can see it's another case actually. So just try as many as problem you can. This is all about the change in flux or induced EMF due to different reasons. One is either B can be changing, another is maybe area is changing, another case is maybe the angle between the B and area vector may be changing. So all these three factors can result in some change in flux through a conductor, through a wire, through a loop, and that ultimately result in EMF induced. So we have seen enough like situations, different cases, try to learn, try to understand the approach, how in every case we need to like start, we need to solve, we need to approach and like get the answer. So this is all about basically like induced EMF. Let's see in the next case, next topic. So thank you so much. This is all about this lecture. See you in next class.